January 4, 1945. Naval Air Technical Arsenal, Yokosuka, Japan. Commander Jiro Horikoshi stood in the engine test facility as mechanics wheeled in what remained of an American fighter plane engine. The Pratt & Whitney R2800 double Wasp had been extracted from a downed Grumman F6F Hellcat, recovered intact from the wreckage of an aircraft forced down on Formosa 8 days earlier. The engine sat on its mount like a trophy of war, its 18 cylinders arranged in 2 neat rows, cooling fins precisely machined into the aluminum cylinder heads. Oil still dripped from cracked lines where the crash had torn connections loose. Battle damage scarred the cowling, but the engine itself appeared remarkably whole. Horikoshi had designed Japan's most celebrated fighter, the Mitsubishi A6M Zero. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. He understood aircraft engines the way a surgeon understands anatomy. He had spent 20 years in aviation engineering, had studied American and European designs, had pushed Japanese metallurgy and manufacturing to its absolute limits. But standing before this captured American engine, he felt something he rarely experienced: uncertainty. The specifications from intelligence reports seemed impossible. 2,000 horsepower from an air-cooled radial engine weighing 2,360 pounds. Japan's most advanced 18-cylinder engine, the Nakajima Homar, produced 1,900 horsepower on paper, though actual field performance rarely exceeded 1,300. And the Homar weighed slightly more than the American engine despite producing less power. The mathematics suggested American engineers had achieved something Japanese industry could not replicate, not because of any inherent superiority in design philosophy, but because of something far more fundamental: material science. Horikoshi ordered his team to begin disassembly. If they could understand how Americans built an engine this powerful, perhaps Japanese designers could close the performance gap before it became insurmountable. What they would discover over the following weeks would fundamentally alter their understanding of the industrial war they were fighting. The story of this engine, and Japan's inability to match it, began not in American factories or Japanese design bureaus, but in the basic chemical composition of the steel, aluminum, and specialized alloys that made modern aircraft engines possible. December 7, 1941. As Japanese carrier aircraft struck Pearl Harbor, American fighter squadrons across the Pacific flew primarily Curtiss P-40 Warhawks and Grumman F-4F Wildcats. The Wildcat, powered by the Pratt & Whitney R1830 twin Wasp producing 1,200 horsepower, was outmatched by the Zero in nearly every performance category. Japanese pilots possessed superior training, superior tactics, and flew aircraft specifically designed to maximize range and maneuverability at the expense of protection and firepower. The combination proved devastating. In the Philippines, Wake Island, and across the Dutch East Indies, Japanese fighters swept American aircraft from the skies. American military intelligence had dismissed Japanese aviation capabilities as inferior copies of Western designs. These assumptions proved catastrophically wrong. Japanese engineers had created in the Zero a fighter that could outclimb, outturn, and outrange anything America could field in the Pacific. Its Nakajima Sakai engine, a 14-cylinder radial producing 950 horsepower, seemed impossibly efficient for its displacement. What American analysts failed to understand was that Japanese engineers had made deliberate trade-offs. The Zero sacrificed pilot protection, self-sealing fuel tanks, and armor plate to achieve its performance. Its lightweight construction and minimal armament reflected Japanese naval doctrine, emphasizing offensive capability over defensive survivability. American doctrine developed differently. Grumman Aircraft Engineering Corporation, designer of the Wildcat, prioritized ruggedness and pilot survivability. Wildcats featured armor plate behind the pilot, self-sealing fuel tanks, and robust construction that could absorb significant battle damage. These features added weight, reducing performance, but kept pilots alive. By mid-1942, after 6 months of combat losses, American naval aviation desperately needed a fighter that could match the Zero's performance while maintaining the protection that kept pilots alive long enough to gain experience. The Navy turned to Grumman with an urgent requirement: design a new carrier fighter capable of defeating the Zero in combat. Grumman's chief engineer, William Schwendler, faced a fundamental problem. The Wildcat's successor needed significantly more power to overcome the weight penalty of armor and self-sealing tanks while matching or exceeding Zero performance. The R-1830 twin Wasp was insufficient. Grumman needed a much more powerful engine. The solution existed, but obtaining it required navigating Army-Navy bureaucratic competition. Pratt & Whitney's R-2800 double Wasp, producing 2,000 horsepower, was already allocated to two critical programs: Republic Aviation's P-47 Thunderbolt for the Army Air Forces and Chance Vaught's F-4U Corsair for the Navy. Both programs faced development delays. The P-47's sophisticated turbocharger system required extensive testing. The Corsair's inverted gull wing and long nose created landing visibility problems that made carrier operations dangerous. These delays freed R-2800 engines for Grumman's new fighter. On June 26, 1942, the prototype XF6F1 Hellcat flew for the first time, powered by the Wright R2600 Cyclone engine, producing 1,600 horsepower. Performance disappointed Grumman engineers. The aircraft needed more power. Navy test pilots had by then extensively evaluated a captured Zero, recovered nearly intact, from Akutan Island in the Aleutians. Flying the Zero against American fighters in mock combat revealed exactly what made Japanese fighters so deadly, and exactly how to defeat them. The Zero dominated slow-speed turning combat, but stiffened at high speeds where control forces became too heavy for pilots to maneuver effectively. Its lightweight construction couldn't handle high-speed dives. The tactical solution was clear. American fighters needed to use superior power and speed, attacking from above in diving passes, refusing to engage in slow-speed turning fights where the Zero's lightness provided advantage. The Hellcat needed power and speed more than it needed maneuverability. On July 30, 1942, the XF6F3 prototype flew with the R2800 engine installed. Performance transformed immediately. Top speed jumped to 380 miles. Climb rate improved dramatically. The aircraft felt solid and responsive. Navy test pilots pronounced it exactly what they needed. Grumman bet their entire production line on the Hellcat succeeding. Production began in October 1942, while the prototype was still completing flight testing. This gamble reflected American industrial confidence and manufacturing capacity. If modifications proved necessary, production lines could implement changes while maintaining output. Japanese industry, operating at maximum capacity with minimal slack, could not afford similar flexibility. The first production F6F3 Hellcats reached fleet squadrons in January 1943. By August, Hellcats were flying combat missions. The transformation they brought to Pacific naval aviation came not from revolutionary design, but from fundamental engineering. The R2800 engine provided power that allowed Grumman to build an aircraft that matched Zero performance in the categories that mattered while providing protection that kept pilots alive. The heart of the Hellcat's capability was the engine. The Pratt and Whitney R2800 double Wasp represented the culmination of 2 decades of American radial engine development and 15 years of continuous improvement in metallurgy, manufacturing techniques, and design refinement. Frederick Rentschler founded Pratt & Whitney Aircraft in 1925 after leaving Wright Aeronautical Corporation. His first engine, the R1340 Wasp, produced 420 horsepower while weighing less than 650 pounds. This power-to-weight ratio seemed impossible to competitors, but Rentschler and chief engineer George Meade had discovered that air-cooled radial engines could match or exceed liquid-cooled designs while offering significant advantages. Radial engines were inherently simple. Cylinders arranged in a circle around a central crankshaft eliminated the complex cooling systems required by liquid-cooled engines. Battle damage that would disable a liquid-cooled engine by rupturing coolant lines merely reduced power in a radial. Damaged cylinders could be shut down while remaining cylinders continued operating. Radials were more survivable, easier to maintain, and could be manufactured in greater numbers with less specialized tooling. The R2800's development began in the mid-1930s as Pratt and Whitney engineers recognized that future military aircraft would require significantly more power. Adding more cylinders was the obvious solution, but creating an 18-cylinder radial that would fit in existing airframes while producing dramatically more power required solving fundamental engineering problems. The primary challenge was cooling. 18 cylinders arranged in 2 rows generated enormous heat. Insufficient cooling would cause cylinder head temperatures to rise, igniting fuel-air mixture prematurely, destroying pistons and valves within minutes. Traditional cooling fin designs, cast or forged as part of the cylinder head, provided insufficient surface area for effective heat dissipation. Pratt and Whitney engineers developed a revolutionary manufacturing technique. Instead of casting fins, they machined cooling fins directly from solid aluminum forgings. Multiple gang saws cut thin, closely spaced fins simultaneously, following the contour of the cylinder head. This created far more surface area for heat dissipation than previous designs. The technique required extraordinary precision. Fins were cut to tolerances measured in thousandths of an inch. The machining process was expensive and time-consuming, but it solved the cooling problem. Each cylinder could reliably handle the heat generated by producing over 100 horsepower, something no previous air-cooled cylinder design achieved. The second critical innovation was materials. The R2800 cylinders were forged from steel alloy specifically developed for high-temperature, high-stress applications. American steel manufacturers had spent the 1930s developing specialized alloys using nickel, chromium, molybdenum, and other elements that improved steel's resistance to heat, fatigue, and deformation under extreme stress. Japanese steel industry lacked access to many of these alloying elements. Nickel deposits in Japan were minimal. Chromium had to be imported. Molybdenum was scarce. Japan's expansion into China and Southeast Asia sought to secure these resources, but submarine warfare and strategic bombing would increasingly cut supply lines. The third innovation was manufacturing precision. The R2800's tight tolerances required machine tools capable of holding dimensions to within a few 10,000ths of an inch. American machine tool industry produced equipment to these specifications in quantity. Workers operated machines that eliminated human error through precise mechanical or hydraulic controls. Parts were interchangeable. An engine assembled in one factory could be disassembled and rebuilt using parts from another factory. Japanese manufacturing relied more heavily on skilled craftsmen hand-fitting components. This produced beautiful work, but it didn't scale. Engines required individual adjustment. Parts were not always interchangeable. Quality varied between factories and between individual mechanics. As the war progressed and experienced workers were drafted or killed, quality declined. The R2800 first flew in a test aircraft in 1939. By 1940, it was producing 2,000 horsepower reliably in flight testing. By 1941, production engines were being installed in P-47 Thunderbolts, F-4U Corsairs, and soon F-6F Hellcats. Pratt and Whitney did not stop with 2,000 horsepower. Engineers continuously improved the design throughout the war. Water methanol injection systems allowed temporary power increases to 2,400 horsepower for takeoff or combat. Improved supercharger designs maintained power at higher altitudes. Better bearings and stronger materials allowed higher operating temperatures and pressures. By 1944, late model R2000, 800 engines could produce 2,800 horsepower using high-octane fuel and water injection. This represented a 40% power increase over initial production models, achieved through incremental improvements rather than complete redesign. American manufacturing capacity scaled production rapidly. Pratt and Whitney operated multiple factories. Ford Motor Company built R-2800 engines under license. By war's end, over 125,000 R-2800 engines had been manufactured. This represented more engines than Japan produced of all types during the entire war. The Hellcat emerged from this industrial foundation as a purpose-built weapon system. The airframe was designed around the R-2800, optimizing cooling airflow, structural support for the engine's weight and thrust, and propeller selection to convert horsepower into performance. The Grumman F6F Hellcat, powered by the R-280010 engine producing 2,000 horsepower, achieved top speed of 380 mph at 17,300 feet. Service ceiling was 37,000 feet. Combat range with external fuel was 300 miles. The aircraft carried 650 caliber machine guns with 400 rounds per gun. More importantly, it could absorb tremendous battle damage and continue flying. 212 pounds of armor plate protected the pilot. Self-sealing fuel tanks prevented fires from bullet strikes. The robust airframe could survive hits that would destroy lighter aircraft. Pilots who flew both the Hellcat and the Zero universally preferred the Hellcat. It might not outturn the Zero at low speeds, but it was faster, climbed faster at altitude, dove faster, and brought them home alive when hit. Combat debut came August 31, 1943, when fighters from USS Essex attacked Marcus Island. Hellcats immediately demonstrated their capability. In the following months, as more Hellcat squadrons deployed to the Pacific, the air combat balance shifted dramatically. The Battle of Tarawa in November 1943 provided the first large-scale test. Hellcats encountered Japanese aircraft attempting to interfere with the amphibious assault. In 2 days of combat, Hellcats shot down 30 claimed Japanese aircraft for the loss of 1 F6F. The exchange ratio shocked both sides. Japanese pilots flying Zeros discovered that tactics which had worked throughout 1942 and early 1943 no longer succeeded. Hellcat pilots refused to dogfight. They attacked from above, dove through Japanese formations with guns firing, used superior speed to disengage, climbed back to altitude, and attacked again. Japanese fighters could not catch Hellcats in a dive. They could not climb fast enough to intercept. Their superior maneuverability became irrelevant when Hellcats controlled the tactical engagement. The Battle of the Philippine Sea, in June 1944, demonstrated complete American air superiority. On June 19th, Japanese carrier aircraft launched 2 massive strikes against American task forces. 140 Hellcats intercepted. When the battle ended, American pilots had shot down 373 Japanese aircraft, while losing 23 F6Fs to enemy action. Japanese naval aviation never recovered. Experienced pilots were killed. Replacement pilots had insufficient training and flew inferior aircraft against opponents flying superior fighters. The Hellcat, powered by an engine Japan could not match, had secured American command of the Pacific skies. January 4, 1945. Yokosuka Naval Air Arsenal. Commander Horikoshi watched as his engineering team completed initial disassembly of the captured R-2800. They worked methodically, measuring each component, photographing assemblies before separation, documenting everything. The supercharger came off first, revealing the 2-stage, 2-speed design that maintained power at altitude. Japanese engines used similar supercharger principles, learned from American Wright aeronautical designs in the 1920s, but American execution was far more sophisticated. The gearing was precise, the impeller blades carefully shaped, the housing machined to tolerances Japanese factories struggled to achieve. Next came the cylinders. Removing the first cylinder required careful work. The cooling muffs, shrunk onto the steel cylinder barrels, had to be heated to release their grip. When the cylinder finally separated, Horikoshi examined it closely under workshop lights. The cooling fins were extraordinary. Thin as paper, they covered every surface of the cylinder head with barely any space between them. Running his finger across the fins, Horikoshi could feel the precise machining. Each fin had been cut from solid metal, with such accuracy that the surface felt almost smooth, despite the thousands of individual cuts. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. He called over his chief metallurgist, a specialist who had studied steel composition and heat treatment for 15 years. The metallurgist examined the cylinder barrel, testing hardness with a portable gauge, examining the surface finish, studying the alloy composition through spectroscopic analysis. "The steel contains nickel," the metallurgist said quietly, "more than our engines use, chromium also, and molybdenum. The alloy is specifically designed for high-temperature applications." Horikoshi understood immediately. Japan's limited access to these alloying materials meant Japanese cylinder barrels used inferior steel that could not withstand the same temperatures and pressures as American engines. This was not a design problem. This was a resource problem. They disassembled the crankshaft next, a massive forging that connected all 18 pistons to a single rotating shaft. The forging was perfectly balanced. Each journal where connecting rods attached was machined to precise dimensions. The surface finish was mirror smooth. Pratt and Whitney had used hardening techniques that made the surface extraordinarily resistant to wear. Japanese engine crankshafts suffered persistent problems with durability. The Nakajima Homare, Japan's most advanced 18-cylinder engine, experienced frequent crankshaft failures in field service. Engineers attributed this to inadequate heat treatment, but the fundamental problem was material quality. Japanese steel lacked the alloying elements that would have provided the necessary strength and hardness. Over the following 3 weeks, Horikoshi's team completely disassembled the R2800. They measured every dimension, analyzed every material, tested every component. They assembled a complete technical report with detailed drawings and specifications. The conclusion was inescapable. American engineers had not discovered secret technologies unknown to Japanese designers. The R2800's design incorporated principles Japanese engineers understood. The difference was in execution. American metallurgy was superior. American manufacturing precision was superior. American quality control was superior. Most damning, American industrial capacity allowed continuous improvement. Pratt and Whitney could afford to test engines to destruction, analyze failures, implement design changes, and production new engines incorporating improvements. Japanese industry, operating at maximum capacity with critical material shortages, could not afford such luxury. Horikoshi compiled his findings into a formal report for Naval General Staff. His assessment was brutally honest. Japan could not replicate the R2800's performance using available materials and manufacturing capabilities. The Nakajima Homare represented the practical limit of Japanese engine development given current constraints. The report circulated through Japanese Naval Aviation Command during late January and early February 1945. Reactions varied from denial to resignation. Some officers insisted that Japanese pilot skill and tactical superiority would overcome American material advantages. Others recognized that no amount of pilot courage could compensate for fundamental industrial deficiencies. The Homare engine, Japan's answer to the R2800, had entered service in 1941 with great expectations. Designed by Nakajima Aircraft Company, it featured 18 cylinders arranged in 2 rows, producing 1900 horsepower on paper. The engine was compact, only 3 centimeters larger in diameter than the 14-cylinder Sakai, despite having 4 additional cylinders. This compact design created severe engineering challenges. Cylinders were packed so tightly that cooling airflow was marginal. The engine ran hot, stressing materials beyond their design limits. Quality control during manufacturing was difficult, because tight tolerances left no margin for error. When Homare engines reached operational units in 1942, problems emerged immediately. Engines overheated in tropical conditions. Cylinder head temperatures exceeded safe limits, causing detonation that destroyed pistons. Valve seats loosened from thermal expansion. Oil consumption was excessive. Reliability was poor. Field modifications and improved maintenance procedures reduced some problems, but fundamental issues persisted. The tight design that made the Homara powerful also made it temperamental. It required skilled mechanics and high-quality materials. As the war progressed, both became increasingly scarce. American submarines strangled Japanese sea lanes. Raw material imports declined. Rubber for gaskets became unavailable, forcing use of inferior substitutes. High-grade lubricating oil disappeared. Fuel quality deteriorated as refineries were bombed. By 1944, Japanese aircraft were burning 92-octane fuel when engines were designed for 100-octane. Performance suffered accordingly. The Homare eventually powered several important Japanese aircraft, including the Nakajima Ki-84 Hayate fighter, considered by many pilots to be Japan's best late-war fighter. When properly maintained and supplied with adequate fuel, the Hayate could match or exceed the performance of American fighters. But such conditions became increasingly rare. American forces captured intact Hayates and tested them extensively. Using high-octane American fuel and proper maintenance, test pilots achieved speeds exceeding 400 miles per hour and were impressed by the aircraft's overall performance. This validated Japanese design capabilities, while highlighting how material and fuel shortages crippled effectiveness. The strategic implications of engine performance extended far beyond individual aircraft capabilities. American industrial superiority manifested in production numbers that Japan could never match. Between 1943 and 1945, Grumman produced 12,275 Hellcats. Pratt and Whitney manufactured over 125,000 R2000, 800 engines for multiple aircraft types. Japanese aircraft production for the entire war totaled approximately 76,000 aircraft of all types. This included trainers, transports, bombers, and fighters. The United States produced over 300,000 aircraft during the same period. The numerical disparity was crushing. Quality amplified the quantity advantage. American aircraft rolled off production lines with engines that worked reliably, using fuel that met specifications, with replacement parts that were genuinely interchangeable. Japanese aircraft left factories with engines that required careful maintenance, using fuel of declining quality, with parts that often required hand-fitting. The human cost of this industrial gap was measured in the lives of Japanese pilots, who flew obsolete or poorly maintained aircraft against opponents in superior machines. By late 1944, Japanese pilot training had been reduced to barely enough hours to master basic flying. Fuel shortages prevented extensive training. Experienced instructors had been killed. New pilots arrived at combat units with perhaps 50 hours of flight time, facing American pilots with 300 hours of training plus combat experience. These poorly trained pilots flew aircraft powered by engines that performed far below design specifications because proper fuel and materials were unavailable. They faced opponents flying Hellcats powered by engines producing full-rated power, supported by unlimited replacement parts, flown by well-trained pilots who had practiced extensively against captured Japanese aircraft and knew exactly how to exploit every weakness. The Battle of Leyte Gulf in October 1944 illustrated the complete dominance Hellcats had achieved. On October 24th, Commander David McCampbell, commanding officer of Air Group 15 aboard USS Essex, led a small group of Hellcats against a massive Japanese strike force. McCampbell personally shot down 9 Japanese aircraft in a single engagement. His wingman, Lieutenant Roy Rushing, destroyed 6 more. In one sortie, 2 Hellcat pilots eliminated 15 enemy aircraft. This was not exceptional luck. This was the predictable result of superior training, superior tactics, and superior equipment. McCampbell would finish the war as the Navy's highest-scoring ace with 34 confirmed victories, all achieved flying Hellcats. The relentless mathematical reality of attrition warfare ground Japanese naval aviation into irrelevance. Experienced pilots who survived early battles were killed eventually through sheer probability. Replacements lacked experience to survive long enough to gain competence. Aircraft quality declined as material shortages worsened. By early 1945, Japanese naval aviation had been reduced to kamikaze attacks because trained pilots in functional aircraft were so scarce that conventional tactics were unsustainable. At Yokosuka, Commander Horikoshi understood these realities better than most. His report on the captured R-2800 circulated through Naval Aviation Command, prompting difficult conversations about Japan's technological and industrial position. Some officers proposed developing a Japanese copy of the R-2800. Horikoshi explained patiently that copying the design was pointless without the materials and manufacturing capabilities to execute it properly. Japanese factories lacked the machine tools to hold the necessary tolerances. Japanese steel mills could not produce the specialized alloys. Japanese supply chains could not deliver consistent quality materials. Other officers suggested focusing on completely different technologies, jet engines perhaps, or rocket-powered interceptors. Small numbers of experimental aircraft might achieve performance sufficient to challenge American bombers. Horikoshi pointed out that such aircraft, even if successfully developed, could not be produced in meaningful numbers. They would consume resources desperately needed for conventional aircraft while having minimal strategic impact. The fundamental problem was not aircraft design or pilot training or tactical doctrine. The fundamental problem was that Japan had entered a total industrial war against an opponent with vastly superior industrial capacity, and after 3.5 years of combat, that industrial gap had become unbridgeable. February 1945. The firebombing of Japanese cities began in earnest. American B-29 superfortresses, flying from bases in the Mariana Islands, attacked urban areas with incendiary bombs designed to ignite wooden buildings. Tokyo, Nagoya, Osaka, and Kobe burned. Thousands of civilians died. Hundreds of small manufacturing shops that produced aircraft components were destroyed. Japanese aircraft industry had relied heavily on a distributed network of small suppliers. Large final assembly plants like Nakajima and Mitsubishi depended on hundreds of tiny workshops producing specialized parts. These workshops operated in urban areas, often in residential neighborhoods, staffed by skilled craftsmen who had learned their trades over decades. The firebombing campaign systematically destroyed this network. A small shop that machined precision gears for engine superchargers burned with its owner's home. A family business that forged connecting rods ceased to exist when the building collapsed in flames. Large factories could be rebuilt, but the distributed manufacturing network, once destroyed, could not be reconstituted. Aircraft production declined precipitously. Engines arriving at assembly plants lacked critical components because supplier workshops had been incinerated. Completed aircraft sat idle, awaiting parts that would never arrive. The industrial ecosystem that supported aircraft manufacturing disintegrated under the weight of strategic bombing. March 1945. American forces invaded Okinawa, bringing land-based airfields within easy striking distance of the Japanese home islands. Hellcats and other American fighters flew from Okinawa, escorting bombers, attacking shipping, destroying any Japanese aircraft that attempted to interfere. Japanese responses grew increasingly desperate. Kamikaze attacks intensified, expending aircraft and pilots in one-way missions. Conventional fighter operations became rare because fuel shortages prevented large-scale sorties. The few operational Japanese fighters that did engage were overwhelmed by numerical superiority and shot down. At Yokosuka, work continued on analyzing captured American equipment. Horikoshi's team examined other engines, including examples from P-51 Mustangs and P-47 Thunderbolts. Every analysis reached the same conclusion. American engines represented a level of material science and manufacturing precision Japan could not match. The Allison V-1710 liquid-cooled engine from P-51 seconds demonstrated superb metallurgy in its aluminum castings. The turbocharger system from P-47 seconds showed extraordinary heat resistance in its turbine blades, made from alloys containing tungsten and other rare materials Japan could not obtain. Each component told the same story. American industry possessed capabilities Japanese industry lacked. April 1945. As Soviet forces prepared to invade Manchuria and American forces consolidated control of Okinawa, Japanese military leadership finally confronted the reality that the war was unwinnable. Some officers advocated fighting to national extinction. Others recognized that further resistance merely increased casualties without changing the inevitable outcome. Horikoshi's technical assessments contributed to discussions about whether continuation of the war served any rational purpose. His reports demonstrated conclusively that Japan could not achieve technological parity with American forces. No amount of determination or tactical ingenuity could overcome the material disadvantage. The question facing Japan's leadership was not whether they could win. The question was how much destruction they would endure before accepting defeat. Every day of continued fighting brought more cities bombed, more civilians killed, more soldiers dying in futile battles. American industrial superiority meant Japanese forces would be systematically destroyed regardless of how bravely they fought. The R-2800 engine had become a symbol of this industrial gap. Sitting disassembled in the Yokosuka workshop, its components laid out for analysis, it represented everything Japan lacked: superior materials, precision manufacturing, quality control, unlimited replacement capacity, industrial depth. Japanese engineers who examined the engine understood they were not looking at superior design genius. They were looking at superior industrial capability. American engineers were not smarter than Japanese engineers. American factories were simply better equipped, better supplied, and operated at far greater scale. This realization was perhaps more devastating than battlefield defeats. Military defeat could be attributed to tactical errors, strategic miscalculations, or unfortunate circumstances. Industrial defeat reflected fundamental economic and material realities that no amount of courage or clever design could overcome. May 1945. Germany surrendered, allowing Allied forces to concentrate entirely on defeating Japan. American aircraft production continued at maximum capacity. Hellcats continued rolling off production lines. R-2800 engines continued accumulating in supply depots. The material advantage that had grown steadily since 1941 had become absolutely overwhelming. Japanese aircraft industry produced approximately 2,300 aircraft in May 1945. The United States produced approximately 9,500 aircraft the same month. This 5-to-1 production ratio meant that even if Japanese aircraft achieved parity in combat, which they could not, attrition would inevitably favor American forces. The Nakajima Homare engine, Japan's best attempt at matching American power output, continued experiencing reliability problems. Fuel quality had deteriorated to the point that engines designed for 92-octane were burning 87-octane fuel, contaminated with impurities. Some aviation fuel was supplemented with volatile oil extracted from pine tree roots, reducing octane to 85 while introducing contaminants that damaged fuel systems. Engines designed to produce 1,900 horsepower were producing perhaps 1,800 horsepower when new, declining rapidly as wear accumulated. Replacement engines were scarce. Repair parts were unavailable. Aircraft sat idle awaiting maintenance that could not be performed because mechanics lacked tools and materials. June 1945. Horikoshi prepared his final report on the captured R-2800 engine. The document ran to nearly 200 pages, including detailed technical drawings, metallurgical analyses, and strategic assessments. The conclusion was stark and uncompromising. Japan could not build an equivalent engine using available resources. The material science gap was too large. The manufacturing precision gap was too large. The industrial capacity gap was too large. Even if Japan somehow obtained necessary materials and machine tools, training workers and establishing quality control procedures would require years. The war would be over long before Japan could close the technological gap. Further resistance was militarily pointless. The only rational course was negotiating surrender on the best terms possible before American forces invaded the home islands and inflicted even greater destruction. The report circulated through Japanese Naval Command during late June and early July. Some officers disputed the conclusions, arguing that Japanese spirit and willingness to sacrifice would overcome material disadvantages. Others, more realistic, understood that Horikoshi was correct. July 1945. American forces prepared for Operation Downfall, the invasion of Japan. Planning documents estimated American casualties in the hundreds of thousands. Japanese casualties were projected in the millions. The invasion would be the largest amphibious operation in history, supported by overwhelming air and naval power. Hellcats would fly from carriers and land bases, providing air superiority over invasion beaches. The aircraft that had dominated Pacific skies since 1943 would ensure Japanese aircraft could not interfere with landing forces. The engine that Japanese engineers had studied so carefully would power fighters that would sweep the skies clear. August 6, 1945. An American B-29 dropped an atomic bomb on Hiroshima. The weapon, representing yet another dimension of American technological and industrial superiority, incinerated the city center and killed tens of thousands instantly. 3 days later, a second atomic bomb destroyed Nagasaki. Between these two attacks, Soviet forces invaded Manchuria, crushing Japanese armies in China. August 15, 1945. Emperor Hirohito announced Japan's surrender in a radio broadcast. The war was over. Japan had been defeated by an industrial power whose manufacturing capacity, technological sophistication, and material resources proved insurmountable. In the Yokosuka workshop, the disassembled R-2800 engine remained on its workbench, a monument to industrial warfare. American occupation forces would eventually catalogue the engine and ship it to the United States for further study, though by then it had revealed all its secrets to Japanese engineers. The lessons learned from examining that engine would influence Japanese industrial development for decades after the war. Japanese engineers understood they had not lost because of inferior intelligence or poor design instincts. They had lost because their industrial base lacked the depth, resources, and capacity to compete with American manufacturing. Post-war Japan would focus intensely on rebuilding industrial capability, emphasizing quality control, precision manufacturing, and materials science. The nation that had lost an industrial war would eventually become an industrial powerhouse, applying lessons learned through defeat to build companies that would compete globally. But in August 1945, those developments lay in an uncertain future. The immediate reality was defeat, occupation, and the task of rebuilding a shattered nation. The R-2800 engine had become part of that story, a tangible example of why Japan lost and what would be necessary to ensure such vulnerability never occurred again. The strategic bombing campaign, the submarine blockade, the island-hopping offensive across the Pacific, all these military operations were enabled by industrial superiority. Aircraft carriers required steel production that dwarfed Japanese capacity. Amphibious landing craft required shipyards operating at scales Japan never achieved. Logistics networks required cargo ships, trucks, and organizational capability far beyond Japanese means. At the center of this industrial ecosystem were products like the R-2800 engine, not revolutionary in concept, but superlative in execution. Built from superior materials using precise manufacturing, produced in quantities that overwhelmed opponents, continuously improved through systematic testing and refinement. American pilots who flew Hellcats often took their aircraft's reliability for granted. Engines started when pilots pushed the starter button. They produced full power on demand. They brought pilots home after absorbing battle damage that would have destroyed Japanese engines. This reliability was not accidental. It resulted from material science, quality control, and manufacturing excellence that represented years of industrial development. Japanese pilots flying Homer-engined aircraft could not take reliability for granted. Engines required careful warm-up procedures. They overheated if pushed too hard. They consumed oil excessively. They failed in combat at rates that endangered missions. This unreliability was not the result of poor design. It resulted from material shortages, manufacturing constraints, and industrial limitations that Japan could not overcome. The industrial war that Japan fought against the United States was decided by factors far removed from battlefield courage or tactical brilliance. It was decided in steel mills that produced thousands of tons of specialized alloys, in machine tool factories that built equipment capable of tolerances measured in 10,000ths of inches, in engineering laboratories that developed new materials and manufacturing processes, in supply chains that delivered consistent quality materials to production lines. These unglamorous aspects of warfare determined outcomes more decisively than any battle. The aircraft carrier task forces that destroyed Japanese naval power were built in shipyards that operated at scales impossible in Japan. The submarines that strangled Japanese shipping were produced by industrial systems that could absorb combat losses and replace vessels faster than they were sunk. The bombers that devastated Japanese cities were manufactured in quantities that overwhelmed air defenses, and the fighters that achieved air superiority over the Pacific were powered by engines that represented the pinnacle of American industrial achievement. The R-2800 double Wasp was not the war's most powerful engine. Larger, more powerful engines existed. But for its combination of power, reliability, and manufacturability, it was unmatched. Over 125,000 were built. They powered fighters, bombers, patrol aircraft, and transports throughout the war and for decades afterward. The Grumman F6F Hellcat, powered by the R-2800, achieved a kill ratio of 19-1 against Japanese aircraft. Hellcat pilots were credited with destroying 5,156 enemy aircraft during the war. This represented 75% of all aerial victories claimed by U.S. Navy and Marine Corps pilots in the Pacific theater. 305 Hellcat pilots became aces, credited with 5 or more aerial victories. These statistics reflected not just pilot skill or tactical superiority, but the fundamental advantage of flying an aircraft powered by an engine that worked as designed, maintained by mechanics with proper tools and parts, supported by a logistics system that ensured availability and readiness. Japanese pilots faced Hellcats while flying aircraft handicapped by fuel shortages, maintenance problems, and declining quality as the war progressed. The captured R-2800 engine that Commander Horikoshi examined in January 1945 told a story about industrial warfare that extended far beyond the Pacific conflict. It demonstrated that modern warfare between industrial nations is fundamentally a contest of manufacturing capacity, material resources, and technological depth. Germany faced similar industrial disadvantages against the Allied coalition. Despite producing technologically sophisticated weapons including jet aircraft, guided missiles, and advanced submarines, German industry could not match Allied production volume. The Messerschmitt Me 262 jet fighter was superior to any Allied aircraft, but fewer than 1,500 were built. American factories produced 50,000 fighters during the same period. Soviet industrial production, relocated beyond German reach after 1941, eventually outproduced German factories despite initially inferior technology. Soviet tanks were simpler than German tanks, but Soviet factories produced them in overwhelming numbers. Quantity became its own quality when the numerical advantage reached certain thresholds. The Pacific War followed the same pattern. Japanese technological capability was real. The Zero was an excellent fighter. The Homare was a sophisticated engine. Japanese pilots were skilled and brave, but these advantages could not overcome the industrial disparity. American factories simply produced more of everything, at higher quality, in quantities that rendered Japanese resistance ultimately futile. The R-2800 engine represented this industrial reality in tangible form. Disassembled on a workshop bench, its components measured and analyzed, it provided irrefutable evidence of American manufacturing superiority, not through revolutionary innovation, but through systematic excellence in materials, processes, and production scale. Commander Horikoshi's analysis of the engine contributed to Japanese understanding of why the war was lost. The defeat was not primarily a failure of strategy or tactics or courage. It was a failure to recognize the industrial requirements of modern warfare and Japan's inability to meet those requirements given available resources. This recognition would shape post-war Japanese reconstruction and industrial policy. The nation that lost an industrial war would rebuild with intense focus on manufacturing excellence, quality control, and technological advancement. Companies like Toyota, Honda, and Sony would apply lessons learned through wartime defeat to build industrial enterprises that would eventually compete globally with American corporations. But those developments lay decades in the future. In 1945, the immediate lesson was simpler and more painful. Industrial warfare favors nations with superior resources, manufacturing capacity, and technological depth. Japan lacked all three relative to the United States. The result was inevitable from December 1941 onward. The only question was how long resistance would continue and how much destruction would occur before acceptance of reality. The Pratt & Whitney R-2800 double Wasp engine, examined carefully by Japanese engineers in the final months of the war, provided concrete evidence of industrial realities that no amount of determination could overcome. It was not a wonder weapon. It was simply an excellent product of an industrial system that Japan could not match. That simple fact determined the war's outcome more decisively than any battle. American industry would continue refining the R-2800 after the war, developing versions producing over 3,000 horsepower for post-war applications. The engine would power cargo aircraft, water bombers, and warbirds for decades. Some remain in service today, 70 years after their design, a testament to engineering excellence and robust construction. Japanese aviation industry would rebuild after occupation ended, eventually producing commercial aircraft and engines competitive with Western manufacturers. But that renaissance required decades of development, foreign technology transfer, and industrial reconstruction. The gap that existed in 1945 could not be closed quickly. The story of the captured Hellcat engine and the Japanese engineers who studied it is not primarily about aircraft or engines. It is about the nature of industrial warfare and the factors that determine victory in conflicts between modern nations. Courage, skill, and tactical brilliance matter, but they matter less than steel production, machine tool precision, and supply chain efficiency. Japan entered the Pacific War believing that spirit and tactical excellence could compensate for industrial inferiority. By 1945, examination of a single American aircraft engine provided incontrovertible proof that this belief was false. The R-2800 sitting disassembled in Yokosuka represented a truth. Japanese military leadership had finally accepted. They were fighting an industrial war they could never win. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.